Hello. This time we are going to learn about stress. So stress has the formula sigma is equal to P over A. That is for normal stress and this is the general equation for stress. Sigma is the symbol for stress value. P here is the load carried by the material. A here is the area in the material that is resisting the load. Now for bearing stress, the same formula is being used, but this time we need to identify the bearing area. And for the shearing stress, it is symbolized by the Greek letter tau, which is equal to V, where V is still the load, shearing load divided by the shearing area. So that is now the three types of stress that we need to study. So for the units involved in stress, what if the value of P here is in pounds and the value of A is in inches, square inches? So pounds divided by square inches, it is pound per square inch, and we can symbolize it as PSI, pound per square inch. Now what if the load here P is in newtons and the area is in meter squared? So Newton divided by meter squared is named Pascal, abbreviated as capital P and A. What if the load here is in newtons and the area here is in millimeter squared? So the unit here, Newton per millimeter squared, is megapascal. So the relationship between Pascal and megapascal is this one. 1 million Pascal is equal to 1 megapascal. So let us now learn about this normal stress. Suppose here I have a table having 4 legs, and these 4 legs have the same sizes, and the load here is at the center of the table such that the load will be equally distributed among the 4 legs. So if the weight here is 40 kilograms on the table, how much load is being carried by each leg? So it means that we need to divide the weight, which is 40 kilograms, by 4, because there are 4 legs, which is equal to 10 kilograms load per leg, but the unit for the load is supposed to be Newton. So we need to multiply the conversion factor 9.81 Newton per kilogram so that we can cancel out kilogram. So the answer would be 10 times 9.81, that is 98.1 Newton load per leg. So P is now equal to 98.1 Newton. What about the area? The area of this leg is specified to be 10 millimeters by 10 millimeters. So it is a square. What is the area of this square? 10 millimeters by 10 millimeters. So the area is 10 times 10, which is equal to 100 square millimeters. So if we are going to compute for the stress, we are going to use the formula stress sigma is equal to P over A. So our P is now equal to 98.1 Newton. That is the load carried by one leg divided by the area, which is 100. So 98.1 Newton divided by 100 millimeter squared. So this one becomes a unit of megapascal. So 98.1 divided by 100, that makes 0.981 megapascal. So that is now the stress of one leg of the table if they are if the load here, the weight here is equally divided among the four legs. So the next type of stress is the bearing stress. The bearing stress can be defined as the compressive stress that is occurring between two contacting surfaces. So to illustrate what bearing stress here, I have two separate bodies. No? So this one is curved and this one is circular. So if I am going to let them touch like that, or in this case it will be like this, and I am going to hold this tube and pull this one to the right, so it means that there is a contact between the surface of this tube with the surface of this bracket here. So what is the bearing stress that takes place here? Because that is where the contact is happening. So if I am going to illustrate, the surface is a curve. Okay, that is a curve, and there is a tube that is going to be in contact with this surface. Now, let this tube have a diameter D, okay? And this one will have a distance L, okay? So if it is like this, it has this distance L. Now, in order to find for the contacting area, we call that one A sub B, the bearing area. In reality, it is a curved area, but we are going to use here the projected area if it is a curve. So what is now the projected area? If that is the curve, then the projected area is this one only. So it is actually a rectangle having this one as D, okay, the diameter of the tube, and this one is L. So the area is now equal to D times L, the diameter times the length there. So we don't deal anymore with a curved surface, but it is the projected area of the surface. So if we are going to compute for the stress, which is P over A, where A sub B, or we can place a subscript there, which is the bearing stress, it is the load, so it is the force that causes this one to be in contact with the other surface, that is the load, and this one here is the bearing area. And if it is a curve, then you are going to use the projected area. So the third type of stress that we need to learn is the shearing stress. The shearing stress has the characteristic that the load or force is acting parallel to the area that is resisting the load. So to illustrate this, I am going to use a small bolt and this bolt is the one that will be sheared when a sufficient force is applied. But before it is being sheared, it will first of all experience a shearing stress. So if I am going to attach this there and held by means of this bolt, and I am going to pull it this way, so it means that there is a tendency that this bolt will be cut in two parts, in two locations, if the force is strong enough to cut this. So this is a case of a double shear, because the shearing stress is found in two locations. So how do we analyze this shearing stress? Now, if this is the bolt, and we are going to attach the middle part here and pull the bolt, pull that part there, and there is a what we call a yoke that will support this one, and pull the other way. So it means that this bolt will be cut into locations. So this is what we call a double shear, because there are two locations of cut. So we can call this one as the V, or the shear load. So the formula was tau, symbolizing shearing stress, is equal to V over A, where A can be, we can place a subscript, A sub S, which is the shearing area. So if we are going to examine the cross section of the bolt is circular. It is circular. The cross section is circular, no? So it means that, what is the area for a circle? The area of a circle is pi d squared over 4. So this is now having a diameter d. Okay, so that is now the area, which is the cross section of that bolt. So if we are going to solve for the shearing stress, so that will be V over 2, because 2 here refers to double shear, times the area, pi d squared over 4. So that will be the equation to compute for the shearing stress in the bolt. What is a single shear? Single means one. Okay, so there is only one part that will be cut. For example, this lap joint, no? If This is now the lock joint. We are going to pull it there with load V, and there's a hole that passes through here, and we are going to place a bolt here. So it means that the bolt will be cut there in one location only. So if this one has a diameter D, so the single shear of this and the stress due to the single shear will be equal to V over the cross-sectional area, which is pi d squared over 4. So no more number 2 here, not like here it has 2. This is only a single shear. This is the equation to compute for the shearing stress of this bolt when it is subjected to single shear only. So those are the 3 types of stresses that we have studied. We have the normal stress, where the force or the load and the area are perpendicular to each other, so perpendicular. The bearing stress is the compressive stress at the contacting surfaces of 2 separate bodies, and the shearing stress here is the load parallel. The load and the area are parallel to each other. Thank you.